Hi everyone, today we're going to discuss difference of squares. So we are continuing our factoring. However, today we are starting with a binomial where the first term and the second term are both perfect squares. Okay, so you can see that we will start with a squared term in each, and then we'll break it down into individual factors. Factors meaning that I have a binomial that is repeated, but the only thing here with these factors is one will be subtraction and one will be addition. Okay, and what that does is it eliminates a middle term. So when all of these are true, then we are allowed to have difference of squares. There must only be two terms. The first and the last must be a perfect square, and it must be subtraction. If this original binomial here that is squared is addition, then we cannot use this difference of squares. All right, so here's what we're talking about. When we look at this problem, x squared minus 25 here, okay, what we notice is that x is squared. That means I have x times x, and 25 should also be a perfect square, meaning what number times itself gives me 25? Or can I take the square root of 25? Okay, so 5 times 5 gives me 25. Okay, it must be a perfect square, meaning that both numbers have to be the same. Okay, so in the front we have the x's. So in my two new factors, or my two broken down or simplified binomials, the x goes in the front of each one, and the 5's go in the back because the 25 was in the back. And as it says up here in the top, one is positive and one is negative. If we took and we multiplied these binomials back together, we would end up with x squared minus 25, and that would be your check that you did it properly. Okay, so let's try example 2 over here. So 81 is a perfect square. That is 9 times 9. And a squared is a times a. Same thing with 49. That is 7 times 7. And b squared is b times b. So when I write my new simplified binomial pair here, the 9a's, the group of 9a, goes in the front of each one. The 7b's go in the back. And just like my problem says, one is positive and one is negative. Okay, so with this setup, when you multiply together, you do not end up with a middle term. You just have two terms, two binomials instead of a trinomial. All right, so with this problem here, okay, we know that x is x times x and y is y times y. So when I put them together, the x's would be in the front, the y's would be in the back, one is positive and one is negative. Now we can see that the answer that I just got was number 3 here. Okay, but notice that number 2 is also a valid answer because it does not matter if the plus is first or if the minus is first, so long as one grouping is the plus and one grouping is the minus. You can see that I just moved them backwards here. They are both valid answers. So remember, the order does not matter. So in this choice, you had 2 answers that were correct. All right. So sometimes you, or most times, you have a number that's not a perfect square, but what we find out is we actually have a GCF. So before you do any problem at all, you want to factor out the GCF because that's going to break it down for you. So first thing on every problem is get rid of that GCF if you have one. All right, so we're going to look here and we have 75x squared minus 12. I know 75 isn't a perfect square, so I want to know, do we have a GCF here? So I made a factor table of 75, 3 times 25, 5 times 15, and then for 12, 2 times 6, 3 times 4. And what I notice is that 3 is a greatest common factor here. So I'm going to factor out that 3 in the front, and then what do I have left? So 3 times what will give me 75x squared? And that would be 25x squared. 3 times 25 is 75. 3 times x squared is x squared. Remember in a prior video, we actually can divide out by the GCF here, and then that is what is giving us the binomial that remains inside of the parentheses here. Okay, 12 divided by 3 is 4, or I could have said 3 times what number gives me 12, and that would be 4. Okay, so at this point, we need to simplify what's in the parentheses. This 3 out front doesn't go away. It's still out front. You can see that down here at the bottom. Okay, 25 is a perfect square and 4 is a perfect square. So 25 we know is 5 times 5, and you can see the 5's come up front along with the x. 4 is 2 times 2, and you can see the 2's go in the back. 1 is positive and 1 is negative. This is what we call fully factored. There's no other GCFs or pieces that I can pull out. That's factored as far as it will go. Okay? Okay, so let's try example 4. 4m squared minus 64. And at first look, some people would say, hey, 4 and 64 are a perfect square. I'm going to do it that way. Okay, but let's first work it with factoring out a GCF. We know that if I went up here and I made a table of 4 and 64, well, 4 is just 1 times 4 or 2 times 2. Okay, 64, whoops, sorry about that. 64 could be 2 times 32, okay, or 4 times 16. So we can tell that right here, 4 is my GCF. So my GCF for this problem is 4, okay? So I'm going to factor that 4 out. And what am I left with? Well, remember, I can just divide by 4. So I am left with m squared minus 16. Okay, and now I need to break down the m squared minus 16. This is my difference of squares. So a set of m's would go up front. And what's 16? Isn't 16 4 times 4? So a set of 4's go in the back. One group is positive and one group is negative. So this is fully factored. Okay, now if you don't do this and you said, hey, 4 is a perfect square and 64 is a perfect square, then what happens, and I'm going to come over here on the right side, so we're just going to kind of separate this off. You end up with 2m minus 8 and 2m plus 8. And what we notice is that I can still break down each set further. I could still factor a 2 out of here. So that's 2 times m minus 4. And I could still get a 2 over here as well. And that's 2 times m plus 4. 2 times 2 is 4. Okay, so we end up with the same answer, but what happens is you have to remember then to pull out your GCF again. So it's easier to pull it out first. If you forget, you can pull it out afterwards, but it makes the problem harder and the numbers larger. Okay, all right, so let's look at this one. Now we have 18c squared plus 8d squared. All right, so if I went up and I created that factor table of 18 and 8, 2 times 9, 3 times 6, okay, 2 times 4. So my largest number here, 2, so that's my GCF. GCF is 2. All right, so I can factor that 2 out. Okay, remember that's just like dividing by 2 if you wanted to, so that would be a 9c squared and 4d squared. Okay, at this point, I have to stop. Look right there. Okay, that is addition. Okay, so if you look at this statement, it says you cannot factor using difference of squares because there is no subtraction. This is addition sign. So right here, this is as far as I could go. That's as far as I could go. Okay, now we see in number 1, it says prime. Prime means that you cannot factor at all, meaning there's no GCF, there's no difference of square, there's no anything. Basically, I can't do anything with it. Okay, that's what prime would mean. So an example of prime would be, for example, we could say 2x squared plus 5. Well, there's no GCF there. There's no difference of squares. Okay, I can't do anything with that. So that's an example of prime. Okay. All right. So on to the last one. Okay, so the first thing we're going to look for is GCF between 25 and 64. This is all 5s. There's no 5s at all. So there is nothing we can do as far as a GCF here. There is no GCF. Okay, so we're just going to break that down just like we see it. So 25 is 5 and 5, and the m's go with it. 64 is 8 and 8. One's positive, one's negative, and if you look, that is number 2. Remember, the order doesn't matter, meaning the positive or the negative. Okay, and that is difference of squares.